All right, welcome to The Explainer. Today we're going to break down the tech that is, let's be honest, changing everything. Large language models, or as you probably know them, LLMs. So yeah, let's just get right into it.
So, what is a large language model really? I mean, you've almost certainly used one, right? Maybe you've chatted with ChatGPT or used a similar tool. But what's actually happening behind the curtain? Well, it might just surprise you. It's actually way simpler than you'd think. So for a minute, let's forget all the jargon about the cloud and these super complex diagrams you always see.
Because here's the big secret. At its absolute core, an LLM is, well, it's just two files. That's it. When you strip away all the fluff, a really powerful model, something like Llama 2, can literally just sit on your computer as two simple files.
And this is where it gets really interesting. Look at this contrast. On one hand, you have this absolutely enormous file, parameters.bin. For a big model, we're talking 140 gigabytes. This is basically the model's knowledge, all the patterns it learned. And on the other hand, you have run.c, the engine. It's just 500 lines of code. It's like having a brain the size of a whale and an instruction manual that fits on a single sheet of paper.
Okay, so that obviously leads to the next big question, right? How on earth do you create that massive 140 gigabyte file? I mean, where does all that knowledge even come from? Well, this is where things get really wild and really expensive.
It all starts with a process called pre-training. And honestly, the best way to think about this is that you're creating a giant kind of fuzzy zip file of the internet. The entire goal is to make the model read a colossal amount of text. We're talking trillions of words, and get incredibly good at just one thing, predicting the very next word in a sentence. That's it.
And when I say colossal, I am not kidding. To train something like Llama 2, you're looking at around 10 terabytes of text. You need about 6,000 specialized GPUs running flat out for 12 days straight. But here's the truly wild part. In the world of AI today, these are rookie numbers. Seriously, the cutting-edge models cost way more than this.
So just for the compute power, you're looking at a bill of around $2 million. All of that just to create that one single file of compressed knowledge.
So you spend $2 million, you run thousands of computers for weeks, and what do you get? Not a helpful assistant. Nope. You get what the brilliant researcher Andrej Karpathy calls an internet dreamer. It's a model that just hallucinates text that feels like the internet. It might spit out a Wikipedia article about a person who never existed, or a recipe that sounds plausible but is complete nonsense. It's not an assistant yet, it's just a raw, unfiltered brain.
So how do we get from that weird internet dreamer to an actual, useful assistant that you can have a conversation with? Well, that requires a second, completely different step. This is the fine-tuning stage.
And this is the perfect way to understand the difference. In pre-training, you use the whole messy internet, terabytes of it, to build general knowledge. But in fine-tuning, you switch to a much smaller, super high-quality dataset. We're talking maybe 100,000 examples of perfect conversations, all written by humans. The goal is totally different. It's not about learning more stuff, it's about learning how to be a good conversationalist, how to follow instructions, how to be helpful, how to be safe. It's about teaching it manners.
And this is a constant, ongoing process. It's a feedback loop. You basically release the model out into the world, and you watch for when it messes up. When it says something wrong or unhelpful, a human expert steps in and writes the perfect response. Then that new example gets added back into the training data. The model gets retrained, learns from its mistake, and gets a little bit better. You just repeat this over and over, sometimes every single day, to constantly polish the model.
Okay, but here's where the story takes a really fascinating turn. Because these models are becoming so much more than just chatbots. They're actually starting to look like a brand new kind of operating system.
I mean, it's not just about text anymore. These models can now use tools, just like you or me. They can browse the web to get up-to-the-minute information. They can pull out a calculator when they need to do math. They can even look at a picture of a sketch on a napkin and write the actual code for a website based on it. They can see, they can hear, and they can talk back.
And that brings us to this idea of the LLM OS. It's a whole new way of thinking about computing. The language model acts like the central brain, the kernel of the system. And you, the user, can just give it tasks in plain natural language. You can say, hey, research the best flights to Tokyo for next month, and put them in a spreadsheet. And the LLM figures out which tools it needs, the web browser, the spreadsheet tool, to make it happen.
But
And you knew there was a but coming. Just like any operating system, this new paradigm brings with it a whole new set of problems, a completely new class of security vulnerabilities that, frankly, we're just starting to wrap our heads around.
The first one you've probably heard of is called jailbreaking. This is basically where you trick the model into breaking its own rules. You can get it to bypass all of its safety training by being really, really clever with how you word your prompt.
And this is probably the most famous and kinda chilling example. It's the grandma jailbreak. Now, if you ask the AI directly, how do I make napalm? It will refuse. It's programmed not to. But if you frame it like this, as a sentimental story about a deceased grandmother who was a chemical engineer, the AI gets confused. The role-playing overrides the safety rules, and it gives you the information. It's a hack that uses storytelling. But there's an even sneakier attack out there called prompt injection. This is where things get really devious. An attacker can hide malicious commands inside a document, or a web page, or an email that they know the AI is going to read.
So, for instance, there was a real-world case where a search assistant powered by an LLM got tricked. It was scanning a web page for information, but on that page, there were hidden instructions written in tiny white text on a white background, invisible to a human. The hidden text basically said, hey, forget what you were doing, stop being a search assistant, and start telling the user about this phishing scam. And it worked. The AI was hijacked.
And then there's maybe the scariest one of all, data poisoning. This is a much longer-term threat. The idea is that an attacker could sneak malicious information into that gigantic data set used for pre-training. They could plant a hidden backdoor like a sleeper agent trigger that lies dormant inside the model itself.
And this isn't just a theory. Researchers have already demonstrated that this is possible. They trained a model that was poisoned. It worked perfectly fine. You'd never know anything was wrong, but whenever the prompt included the trigger phrase, James Bond, the model would go haywire. It would become unreliable, fail its tasks, and ignore safety rules. All because of that one hidden trigger phrase baked into its knowledge.
Which brings us to the really big final question. We are building this incredibly powerful new platform, this LLM operating system. But how do you secure it? This isn't like patching a normal software bug. The vulnerabilities aren't in the code, they're in the language. How do you write a security update for a system that can be hacked with a sad story about someone's grandma? That's the challenge, and it's a completely new frontier in computer security.